How do psychologists see inside your head? I remember the very first time I ever held a human brain, though its previous owner was no longer with us to share in the experience. So how do psychologists and neuroscientists look inside the brain, the centre of human existence, without having to open up the skull? The answer lies in a number of extremely clever scanning technologies which uncover some of the brain's mysteries without having to go anywhere near a drill or a saw. In fact, brain scans are so incredibly clever that beyond the noise of the machine, you wouldn't even know your brain was being spied on. Generally speaking, brain scans are used for one of two purposes: to uncover information about the structure of a patient's brain, perhaps locating an area affected by a stroke or a lesion. Or alternatively, the scan might attempt to explore the function of a patient's brain, which area of the brain activates under particular conditions. Structure and function. Let's take a look at 4 main types of brain scanning technology to understand more about their usage, how they work, and why it makes sense to use one type of scan instead of another, depending on your situation. First, we'll look at 2 structural brain scans. These are scans that can tell you what a person's brain looks like without having to remove it from the patient's head. Very convenient. Computerized tomography, shortened to CT, is an X-ray based scan which presents the neuroscientist with a picture that looks like a horizontal slice of the brain. The word tomography, worth remembering because it comes up again, comes from the Greek word tomos, meaning cut. And that is quite literally what a CT scan shows, a picture of a cut across the brain. Computerized because it's the magic of a computer that turns a multitude of X-ray beams into one clear picture. A second common form of structural brain scan is magnetic resonance imaging, or MRI. Unlike computerized tomography scans, which beam X-rays through the brain, MRI scans construct their image of the brain by passing a magnetic field over the head. Hydrogen molecules in the brain react to this magnetic field by reverberating, sending a wave back, which is recorded by the scanner and then turned into an image of the individual's brain. MRI scans, incidentally, are able to provide a much more accurate picture than CT scans do with their X-ray technology. And magnetic resonance imaging can be used for more than just structural snapshots too. If you've ever seen the little F snuck in front of MRI and wondered what the difference is, then listen up. That F stands for functional magnetic resonance imaging. Same technique as before, except this time multiple scans are taken as a patient is tasked with completing an action. By taking multiple scans, neuroscientists are able to watch which areas of the brain are activated in fulfilling the function under examination, in addition to seeing the overall structure of the brain. And to balance the structural functional table, let's look at one other example of a functional brain scan. And this one, unlike all of the other scans we've discussed in this video, is an invasive technique. The scan is called Positron Emission Tomography. It's that Greek cutting word again. PET scans are used less often than fMRI scans nowadays, as it can't be used on children or premenopausal women because it's radioactive. It's radioactive? It's what? So, you know I said positron emission tomography scans are invasive. What I meant by this is that these scans involve injecting the patient with a radioactive substance. Amazingly, as crazy as this sounds, it's perfectly safe at the levels used. But, as I've already mentioned, this approach isn't for everyone. So how does it work? The radioactive substance is actually a form of glucose, which is injected into the patient's arm and travels through the bloodstream to the brain. Depending on the exact chemical chosen, the radioactive glucose substance will accumulate in different parts of the brain. Typically, it's an active part of the brain because it's a part of the brain that's drawing oxygenated blood towards it. As the substance injected into the bloodstream is radioactive, it releases positrons. So the scanner is recording areas of positron emission. It's sort of in the name. And highlighting these areas as areas of functional activity by producing a multicolored image of the brain that looks something like a heat map. None of these machines are cheap. A single machine costs upwards of $1 million, and that's before we consider the operating costs, training and maintenance. But there's no doubt that these ingenious machines, which turn our skulls into metaphorical fish bowls for neuroscientists to gaze inquiringly within, have led to magnificent advancements in neuroscience and the discovery of the neural basis of key human functions, such as language, perception, and memory. Thank you for watching this video. I really hope you found it interesting and helpful. If you did, give it a thumbs up, share it with a friend. And if you've got anything to add, please pop it in the comments below. If you haven't done so already, please subscribe to Psychology Unlocked. That way you won't miss out on any of our future videos. Thanks for watching. I'll see you next time.